The Bitcoin, Ethereum, and Blockchain Super Conference is coming to Dallas, Texas, February 16, 17, and 18 in 2018. If you know of a better way to get the latest insider knowledge about crypto, to hear directly from the top minds in this field, to interact personally with 800 fellow crypto lovers, hodlers, investors, miners, traders, developers, and founders, then I'd like to hear about it. If you don't, then you don't want to miss out. Register today for the Bitcoin, Ethereum, and Blockchain Super Conference. Go to bitcoinsuperconference.com and register today as a super early bird to get the lowest rates on tickets and hotel rooms. That's bitcoinsuperconference.com.
Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with Future Tech Podcast. My guest today is Jeff Bilmes. He's at the University of Washington. Jeff, how you doing?
Pretty good. How are you doing?
Yeah, thanks for coming. Brief intro of who you are, and let's talk about the research and the projects you're working on. Melody.
Sure, sounds good. So I'm a professor at the University of Washington, Seattle, in the Department of Electrical Engineering, and I've been working on machine learning and AI for about the past 25 years. And
wow.
A couple of different applications of machine learning, including things like speech recognition and computational biology and non-speech but voice-based human-computer interfaces and things like that, but also a lot of sort of what maybe you could call pure machine learning technology. The thing that I've been kind of excited about lately is essentially technology to try to understand how you can measure information and data, or something what I like to call the science of information management. And what this is stuff that allows you to take very, very large data sets and information, large data sets that contain a lot of information, but then make them more efficient so that they express the same information but much more efficiently and without the size. So it's kind of like big, small but still informative data, unlike big data, which is big and informative. This is like small but still informative data.
Well, you're talking about training data necessary to train an AI. I've heard that tons of data is needed, or is it if you just have countless millions of points of data, instead of having to use it all to get a representative sample or answer, you could use a subset of it or a smaller amount.
Yeah, that's exactly right. So, the thing about, data, data is one of the critical things that has enabled machine learning and AI to be successful. And one of the things about big data is that it's also very redundant. And, for example, there's not a lot of information if you have the same photo duplicated many times, but there's many other kinds of redundancy besides just duplication of data items. It could be things, you might have pictures of trees, and it might be the same kind of tree or the same angle of the tree or the same time of year, and you don't actually need as many photos of that particular kind of tree. But the concepts themselves might actually not be things that humans are good at recognizing, like, for example, a tree. There might be other sort of deeper concepts that the data expresses redundantly. And the question is, it's not really efficient to actually have all of that information expressed redundantly in a data set when you can actually reduce it in some way while still preserving the information, so you can actually produce a useful machine learning system, but much more efficiently. So that's sort of what I mean by the science of information management.
Well, what's a specific example that you're working on in the lab? Are you looking at machine vision, and instead of having to show the computer 8 million pictures of cats, you can somehow show less? Or what are you working on specifically?
You definitely don't need 8 million pictures of cats to understand what a cat is. Humans do it without very many images of cats. They can very quickly, small children can recognize a cat only after seeing maybe one or two examples. But yeah, that's the kind of thing. It's not just machine vision or computer vision. It's we've applied this approach, this kind of stuff to speech recognition and to statistical machine translation and to proteomics, trying to understand the proteome, and also to genomics, trying to understand the human genome, and also to smart city data. And basically any kind of data, any type of modality you can imagine generally is faced with this kind of problem, the problem of redundancy. And it really makes producing machine learning and AI systems much more expensive than it needs to be. And so in some sense, you could sort of think of this as basically, finding good solutions, finding good machine learning systems faster and more efficiently than you'd be able to do otherwise. And possibly because you can find them faster and more efficiently, you can do more of an exploration in a given amount of time. And so therefore you can, if you have the same amount of time and the same amount of compute power, you can actually find something better because you do more with the same resources as you would otherwise.
But data has a cost, so I guess the less data you have to get, the cheaper it could be. And then there's processing time. So again, the less data you have to process, the faster you can process to get to a solution.
That's right.
Any other factors missing that would benefit
there's also
from this
different
process?
kinds of data. Yeah, there's like labeled data. Labeled data is particularly difficult to get because you have to have humans go in and look at the data and tell you what it is before you can use it in a machine learning system, and that's also costly and error prone. So if it's the case that you can get humans to only label the necessary data, the data that you actually need, and that's not redundant. You don't want humans to go around labeling stuff that you already know about because that's pretty wasteful and expensive. So it's not just reduced compute time, it's reduced dollars and reduced search time, so you can actually find a solution faster.
Any other things that more efficient data will do? Any other benefits?
Yeah, there's a couple of things. Like, one sort of task that I'm hoping to address someday is things like medical tests. Like, let's say that you've spent $1 billion developing a new drug of some sort, and you'd like to test it on a population, but you want to make sure that the drug doesn't have any adverse effects on any subgroup within the population. And so you could, for example, take a random sample of the population and check, and if it all works out, that's okay. But there's no guarantee that random subset of the population is representative of the whole population. There might be some subgroup that you miss, because when you take a random sample, you have no guarantees that you're going to catch all the corner cases. And if you come up with, say, a way of, you can think of this as essentially a population and their genome, say, as a large data set. And if you come up with a representative subset of the data set, and in this case, a representative subset of the population, you can be more sure that there are no corner cases that you've missed. And the drug that you've spent a lot of time and effort developing will, have more assurances that it's safe. So that's something that actually could potentially have some real societal benefits, I think, at least in the medical community.
So how do you make data processing more efficient? The algorithms, or is it other basic concepts? Like, what kind of toolkit have you developed to do this?
Well, so it's something that we've been working on for, I guess about 15 years or so, but it's right now beginning to blossom into a lot of different areas. But it's basically using the mathematics of information on data sets, and it's something that ordinarily would be computationally very hard to do, but thanks to the properties of this particular set of techniques, it's actually not computationally infeasible to come up with good subsets of data. The particular, I've been working a lot. I'll just tell you the name of the methods. It's called submodular optimization, submodular functions, and you can think of it. It's sort of, on the one hand, it's an old technique, but it's relatively new in machine learning, and it's something that, you've heard a lot about, for example, deep learning and modern AI techniques, and this is something that's compatible with all of those methods because it essentially can be used to make any machine learning method more efficient in that way. And we've developed a lot of algorithms for it, which are pure algorithmic stuff, purely algorithmic developments, and also we've developed a bunch of software and a bunch of strategies for applying it to different types of data.
Okay, so any examples of data collection and processing you've made more efficient that are out there in the wild, and what are some of the beneficial numbers? Can you contrast them before and after, speed, time, number of data pieces, et cetera?
Yeah, well, I guess the best way to answer that question is to go look at my publications page. Being an academic, of course, everything's in the publications. But, it's a sort of a trade-off because, let's say you have a data set. Let's just make it concrete by giving you an example of, let's say that there's 100 data items. There's sort of a quality size trade-off. Like you might say, I can only afford, in terms of compute time or some sort of budget, to have 10 data items. So that turns into a problem of how do I find the 10 most representative data items out of those 100, right? And so in that case, you get a factor of 10 improvement in efficiency and speed because you're using a factor of 10 fewer data items than you would otherwise. There's another approach where maybe you're more quality conscious, and you might say, okay, I don't have any cost limit, but I still want to save as much in terms of cost as possible. But quality is the primary thing I'm concerned with. And so you might say, find me the smallest data that preserves 96% of the quality, in which case it'll say, okay, here's the 27 items out of those 100 that preserves 96% of the quality. And then you say, great. And then you just use them, in which case then you get like a factor of 4 reduction or factor of 4 improvement in efficiency.
Yeah, it sounds like design of experiments where they do fractional at a fractional amount of parameters, but they want a certain confidence level in the results. It sounds exactly like that applied to data.
In a certain way, yeah, it is similar to that. But the question is, how does one do it? And actually, and we're using machine learning and AI. It's interesting because the way that we achieve this is by using some of the strategies of machine learning and AI to actually produce the algorithms that can then reduce the sizes of the data sets, which then can be used in subsequent rounds of machine learning and AI systems to self-referential in a certain sense.
What's it been like for you to be in this field for 25 years? I mean, did you come to did you run into a lot of brick walls for a while? It seems like AI, for some reason, just recently is blossoming. What do you think? Why are there breakthroughs now when for so long it seemed to go quiet?
Yeah, it's interesting, actually. It's a good question. So one of the things that's interesting is just even the language on how we refer to AI has changed. AI has now become a count noun, where you can talk about an AI or two AIs, or let's combine several AIs together into one AI. It used to be the case that AI was a mass noun. Like, for example, the word confidence is a mass noun. You can't say two confidences, but the word book is a count noun. You can say two books. And AI used to only be a mass noun. You could say things. And I still use that language. I say we use AI techniques or AI types of methods to solve a problem. I never, for example, use the language 3 AIs is what it takes to screw in a light bulb, for example. But basically, other than the language change, the question is, really, what is AI? And I'm probably going to disappoint you in a certain sense, because I don't think really AI is anything different than standard computer science. It's basically just a set of techniques that enable computers to do more things, just like any branch of computer science. Like database technology allows computers to do databases, and optimization methods allow you to optimize, and AI allows you to do more things. But in this particular case, AI allows computers to do things that, tend to be things that humans do, like understanding images or recognizing speech. And there's a lot, actually. I mean, I've never, like you used the word brick wall or roadblock. I've never, in this time I've been working in this field, felt like there was a roadblock. But you're right that in the past couple of years, there's been a lot more interest in AI. And I think that that's going to continue. I mean, I think AI is going to become increasingly more important, but it's for the same reason that computers will become more important and integrated in our lives. And the reason why is because we're going to want computers to solve more and more tasks to, hopefully and ideally make our lives better. But this is not really anything different than what's happened before. I mean, historically, computers were used to make our lives better by solving things like financial calculations or maybe physical simulations, or solving problems in manufacturing or operations research. And then, in the 70s, computers became more personal, and things like word processors and spreadsheets, and then, entertainment kinds of things happened, computer games. But, what's happening is as computers are becoming more powerful, the tasks themselves are becoming more complex, and the code needed to get computers to solve those more complex tasks are also becoming correspondingly more complex. And so what's happening is that, humans themselves, we are not really getting much smarter, but the tasks and the corresponding code to solve those tasks are becoming more complex. And so our humans' ability to solve these tasks, effectively and efficiently and in a timely manner is reduced. And so what is machine learning really? And what is AI? Or what machine learning sort of leading to AI basically is the following. It's basically, it's rather than actually solving a task directly by computer, by having a human write a program to solve a task, what we're doing is we're writing a program that itself learns how to solve another task. So this is really, in some sense, a form of indirection. And again, this is nothing new. You're probably familiar with the famous quote by David Wheeler, I think, that said that all programs or all problems in computer science can be solved by one more level of indirection. So machine learning is just another instance of this. We're doing indirect algorithms. So I think that rather than calling it AI for artificial intelligence, what I think we should be calling it is indirect algorithms, because we're writing programs that write programs to solve tasks. And the way that it's done is using data and optimization. So you asked the questions like, why has there been such a success in machine learning the past couple of years? So I think that there's really, in some sense, three things that have changed, maybe in the past 10 years, maybe a little bit sooner, but basically three things have come to pass that have changed this. First is, there's big data. I mean, people don't talk about big data that much anymore, but big data is still here, right? Big data is big and getting bigger, and it's going to keep getting bigger. And not only that, but it's, related to the stuff that, my own research is about. There's also big information, right? So there's a ton of information in the big data, but maybe it's not being represented that efficiently, right? So there's big data. The second thing that has enabled machine learning is that there's just massive amounts of commodity vector supercomputing, in the form of graphics processing units, GPUs. What's amazing to me, I mean, having worked in computer science for a while, is that you can, for less than $1,000, you can get an 11 teraflop GPU card. That is truly amazing. 11 teraflops is not even conceivable in terms of how much compute that is and what you can do with that kind of thing. So those kinds of commodity supercomputing cards that you can get very cheaply have changed things. Now, the question is, why does this happen? One of the things that people don't talk about that much is essentially in the 1990s, there were teenagers wanting to play video games on home computers. And these teenagers essentially created a mass market for commodity vector coprocessors. And they're the ones who enabled firms like NVIDIA in the early 90s to get started. And then NVIDIA invested massive amounts of money to create essentially economies of scale for this kind of commodity supercomputing. So I think that we owe the AI revolution as much to teenagers in the 1990s playing video games as we do to anything else. Because if it wasn't for the ubiquity of commodity supercomputing, this wouldn't be happening right now. Then, of course, the third thing, which is what everybody's talking about these days, is deep models. And essentially what that really is an expressive family of mathematical models. And there's two things about them that's really important. One is that they're expressive, meaning that they can do a lot of things. You can get them to solve a lot of problems. But the other critical thing, which folks are not talking about as much, is that they happen just by chance to perfectly fit the type of computing that's provided by GPUs. And that's basically matrix computations. So neural networks and deep neural networks and all that kind of stuff basically require vast amount of matrix computations. And that's exactly the kind of computations that GPUs can do really, really efficiently and really cheaply. So if it wasn't for that, if it wasn't for the fact that this particular class of models, deep models, fit with GPUs and that we have tons of data to train it on, none of this would be happening, I think. So nothing really remarkable is going on, I'm sad to say. And in some sense, it's really simple, but that's really, I think, what's happening.
So it's an aggregation of several factors that seem to be coming all at once now that's accelerating things.
Yeah, that's right. So there are some really important issues in AI, however, there's a lot of discussion about AI in society, and there are some critical issues that we still have to solve. I can talk about them if you want, I think. Yeah,
let's talk about, what do you think are the either potential downsides or like the biggest issues that, if more successful, which it probably will be, what's AI going to disrupt in your mind?
Well, it's already in some sense disrupting a lot of things, but there are a couple, so one of the things I don't think we're in any danger of there happening is any sort of AI smart robots taking over the world. That's basically just science fiction. And you do hear a lot of the popular press talking about the science fiction of artificial intelligence, and you see movies and science fiction books and everything, and that has been going on for a long time. But what essentially AI machine learning is new capabilities. And so one of the things that well, there's a couple of things actually we need to solve. Like one is sort of the liability issue. You've heard a lot about self-driving cars, and the technology in some sense is mostly here for a car to drive around by itself and be pretty safe, arguably safer than a human driver. But the question is, when an accident happens, at some point, a self-driving car will cause a mass fatality event. And the question is, who is liable? Is the person liable? Is the designer who architected the model itself, the person who set up the deep model? Or is it the person who wrote the toolkit that then learned that model? Or is it the organization that supplied the self-driving car data? Or is it maybe the person who developed the mechanics of the car? Or maybe it's the lawyer or the politician who said it was okay to put that self-driving car on the road? Who amongst those five entities should be held responsible, or maybe some combination of all of the above? I mean, the problem is like our current notion of liability, that the driver, when there's an accident, the driver of the car is held responsible. The liability laws need to change and need to evolve. And right now, liability laws might be one of the critical things that are holding back self-driving car technology from hitting the road en masse. And actually related to that is interpretability and accountability. So like you have a massive trained machine learning system that does fantastic things, and it's got maybe hundreds of millions of parameters in it. So how do you interpret that? How do you understand, why did it say what it said? Why did it recognize that image as a cat? What about that cat made it recognize it as a cat? I mean, we need, rather than black boxes, we need to treat them as transparent boxes. And in fact, actually, there's a group at Google called Glassbox that's specifically trying to make machine learning methods more transparent. And there are other people in the research community as well, and the people who are spending their research careers on trying to make machine learning systems more transparent.
Yeah, I've heard, machines talking to each other came up with their own language that wasn't really decipherable by outsiders. It seems like machine intelligence actually is a real thing, and machines sometimes are finding solutions to problems that people never found, and they sometimes don't understand how the machine got there. So it's not just transparency into everyone understanding how it works, but literally understanding how did it do that.
Exactly. That's exactly right. And that's a research problem. That is what we need more research in order to solve, because these are very complicated models. They're, like I said, hundreds of millions of parameters, maybe even more. And the question is, for things like accountability and liability, there needs to be ways to try to understand them. Now, actually, one advantage that we have with machine learning produced models over, say, for example, trying to understand the human brain, is that we can kind of mess with models without disturbing what they do. Like there are many people, in the neurobiology field who will try to understand brains of animals by looking at the way a single or a small group of neurons responds to visual stimuli. But the problem is that as soon as you put in a probe on a neuron, you change the way it behaves. With a big neural network, you can actually see the activation functions at any given layer, and you can look at what it's doing in response to an input without actually changing what it ends up doing with those activations later on in the network. And so there's a huge advantage. And so I believe this is a very surmountable problem. This is something that we're going to have no trouble solving in the future, unlike, for example, understanding the human brain, where just by observing it, you're changing its behavior. But what's related to that also is that we need to make sure that algorithms, by them being transparent and interpretable, we need to make sure that they're fair and they're unbiased, and that even if there are unintended biases in the data, that the resulting machine learning system doesn't reflect those biases. Another thing that is also somewhat related to what you just said is this notion of adversarial examples, or maybe what you could call artificial illusions. Illusions for artificial intelligence systems. And that's where many people have shown that you can take images, or folks at Kyushu University in Japan, or at Berkeley, or at Google, they're creating instances of images that to a human look perfectly fine, and you would never recognize a dog as anything other than a dog, but you might change one pixel and you've changed the response. You change what a neural network does with it. Or you change a speech utterance to sound perfectly fine for a human, but then the machine learning system does something completely wacky with it. And those adversarial examples are really, I think that's really important research, because basically in order for these systems to be deployed in the wild, they need to be reliable, robust, and stable. And if it's the case that it's so easy to fool these things with adversarial examples, then they're not going to be reliable and we can't trust them, stable. So it's not like, it's also similar to, humans have illusions too. There's many optical illusions and illusory contours. The difference again is that in a machine learning system, we have the objective function. We can actually drive the objective function to change the input so that the input transforms into one of these adversarial examples. And that's only because we have access to the thing that actually produced the machine learning system, and we have access to do mathematical manipulations through the parameters of the model into the input. With a human, you can't do that. So you can't, for example, drive through the human brain a given visual stimulus into an illusion. That doesn't work. So it's just something that has to be, again, this is a research, I think this is a research problem, and I think it will be solved eventually. A couple of other really important problems, however, with AI, this is more sort of AI in society, and that's sort of trying to understand truth and trust. And, you've heard about fake photos done with Photoshop for a long time. And even before then, there were things like the special effects industry in movies has been producing, amazing but not real visual effects that we were told are fake. And even going further back, there were things like the Mechanical Turk, which was a fake chess playing machine back in the 1700s. That's actually really it's a really important issue. And I think there, for example, it's not clear that there's a good solution for that, because at some point, probably in the near future, it's going to be impossible to tell the difference between a real photo and a fake photo, or a real video and a fake video. So it's no longer going to be the case that seeing is believing. And we'll still, however, want to achieve truth, or at least to understand the difference between what's fake and what's real. Right. So somehow we need some sort of new trust mechanism. And it's kind of interesting that here we are in this relatively speaking advanced age with modern technology, but what this technology is going to do is bring us back to the time when truth is achieved without photos or video, because people, used to have to come to a belief without ever seeing something with a photo or video. And soon we're going to get back to that point, because, you'll see a video of it and you'll say, I don't know, maybe that's real, maybe that's not, I don't know. So there needs to be a new form of achieving truth. And that's, I think, particularly important in the current, political world as well.
Yeah, it could be a big problem. Mark Goodman, who did the book Future Crimes, talks about this. And, what's on the screen is real, and people can be deluded into all kinds of things. So it could be a very dangerous thing.
Yeah, and that's very different. This kind of danger, I agree with you. I think this kind of danger is very different than, say, AI robots taking over the world. But it's more sort of it's humans. It's what humans do with the technology that they have. And it's very similar to the atomic age, where humans built this capability, and the atomic atomic technology and atomic energy, and what humans do with this technology will really determine their own fate. And I think it's very similar to, in this case with AI, what humans do with AI will determine their own fate, but not in the same sense as, robot overlords in the Terminator sense taking over the world, but it will be more things like, how do we achieve truth, which is maybe a bit more mundane sounding. So another thing that I think AI is really, there's a lot of discussion about AI and machine learning in the sense of human jobs, and whether or not jobs that are traditionally done by humans will be overtaken by automated machines. And I think that is something that's very important, but it's also something that's very old. And I think since the Industrial Revolution in particular, there have been many mechanisms that have replaced jobs that have previously done, going back to the printing press and various forms of manufacturing and things. And that kind of changes, I think it's inevitable. And I think we should expect it. And more importantly, I think we should prepare for it and overcome it, because there's no way to avoid it. And I think that the solution to that problem, I think there is a good solution. And that's basically to sort of expect that we will have to spend our lives continuing to learn. It's sort of like a lifelong learning. And as being in a university, I like to think that, getting an education is important, but one of the most important things about an education is not just knowing what you need to know for the current, say, AI-enabled society, but you need to know how to learn. You need to learn how to learn. And if you spend your time learning how to learn, then you're setting yourself up in your life to be able to adapt to changing environments. So that's one of the things I actually always tell my students, which is that, I'm teaching this stuff in this class, but most importantly, what you should be thinking about while you're learning is how are you learning what you're learning? And can you sort of adapt, and can you learn to understand what are the strategies that you've used to learn these things more efficiently, so that in the future, when you encounter something that's completely different, you can learn something else faster and better, and more efficiently, and memorize it better. And that, I think, is something that educators should be teaching a lot. We should be teaching not just stuff, but we should be teaching how to learn stuff. And I think that will actually help, because then, given that change is inevitable, the way you overcome it is by realizing that, okay, well, every couple of years you're going to have to essentially go back to school or be a lifelong student. And that's something that I personally try to do, is I try to think of myself as a student, and I'm constantly trying to learn new things. And I think by constantly trying to learn, you sort of keep that learning open to new ideas and open to learning as an option for you. And I think that would help a lot to address this one issue.
Well, Jeff, very good. We're just about out of time. So the last question I want to ask is, for people that want to get in touch with you and find out more about your research and get involved, how can they get in touch with you? What's the best way to do it?
Well, the best way is to do a web search and to search my name, and my email address is online. You can just send me an email. Okay, very good. So just Jeff Bilmes, University of Washington professor, and then people should find your info? That's right. Okay. Well, very good, Jeff. I appreciate you being on, and it's going to be interesting to see what goes on in AI in the near future. It's going to be hopefully amazing. Yeah, I think it will. Thanks for inviting me. Appreciate it. It's fun.
The Bitcoin, Ethereum, and Blockchain Super Conference is coming to Dallas, Texas, February 16, 17, and 18 in 2018. If you know of a better way to get the latest insider knowledge about crypto, to hear directly from the top minds in this field, to interact personally with 800 fellow crypto lovers, hodlers, investors, miners, traders, developers, and founders, then I'd like to hear about it. If you don't, then you don't want to miss out. Register today for the Bitcoin, Ethereum, and Blockchain Super Conference. Go to bitcoinsuperconference.com and register today as a super early bird to get the lowest rates on tickets and hotel rooms. That's bitcoinsuperconference.com.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.